Welcome to everybody. My name is Marco Aspromonte and I'm here to explain my work about neural radiance field for view synthesis of arbitrary objects. NeRF is an innovative architecture that is useful to render three-dimensional objects starting from two-dimensional images. Its behavior is quite atypical in computer vision and deep learning fields. First, because we are typically defining a transformation of a five-dimensional input, which involves x, y, and z standard coordinates, plus theta and phi, that are the coordinates to express viewing directions. Such transformation brings to a four-dimensional output, in which three dimensions are for RGB channels and one is for density sigma. Therefore, NeRF models are very expensive in terms of computational effort on GPUs, and many times we need to allocate a very large amount of data, since we are not dealing with any transformation on the input and during the training. In fact, there aren't convolutional layers, for example. So, my objective is to make this architecture lighter in order to render arbitrarily chosen objects. The most relevant competitor in this field is Lombardi with his neural volumes, which consists of an encoder-decoder network that transforms input images into a three-dimensional volume representation. However, it is not better in terms of computational effort, and moreover, the result is worse under high frequencies of movement during the visual exploration of the renderized object. However, until now, we know that NeRF architecture requires high computational cost and few days of training. It often takes between 10 hours to several days to model a single scene at moderate resolutions on a single GPU. So it seems that if we want to exploit this approach for a personal task achievement, we need to allocate a large amount of data on a GPU without any time limitation. And that is the point. People, often students like me, typically employ cloud computing with free licenses, so it is not possible to explore such model in such context. But fortunately, there are the so-called tiny NeRF models that are trainable in less time, even if they usually accept very well acquired and medium-low resolution images. Since our image's resolution is a bit limited, and in any case our GPU is not able to allocate samples with resolution higher than 1024, instead of rendering a complete scene, we can focus on a single object. That in my case is my pet fossil dinosaur called Rhino, acquiring 55 samples from different viewing directions, trying to keep focused the center of the objects. My method was a bit Spartan. I used a cut potatoes tube to put the phone inside, in order to have a fixed level of height, and I acquired the photo following the perimeter of the circle drawn around the object. However, in the acquisition phase, I had to deal with the background that propagates noise during the training phase. So I decided to put a preventive step to remove it, with a UNet architecture that performs semantic segmentation. The UNet gives as an output a binary mask that is then used to compute a bitwise AND operation with OpenCV, in order to keep only the subjects. And the background pixels are set to 255. Another important aspect is that in the most of the cases, specially created datasets reserve information about camera poses and focal length that in normal cameras are not known a priori, but we can estimate them. I used a model that estimates camera poses and focal length from Active Vision Lab repository. The most, we keep the direction of the circle, and the center of the subject during the acquisition phase, the more rototranslation parameters and focal length are goodly estimated. Rototranslation parameters are estimated considering the axis angle representation, starting from the instantiation of an identity matrix. Focal length is estimated by picking the last value of all the focal lengths computed during the estimation phase along x and y axis. It is initialized with the dimension of the images, so with the height set to 1024. Then we can use such estimated parameters to complete our training dataset. So we can now feed the samples to the tiny NeRF architecture. NeRF architecture, standard architecture, is usually structured with 8 sequential layers. And if we not count RGB and density layers for the output, which are concatenated at the end of the network to return our 4-dimensional output. But here we are dealing with the 6 sequentially fully connected layers in order to reduce the computational cost. Also, it is not necessary to monitor a loss function with respect to a validation set with few images, but we can take just one additional validation sample to check the behavior of the PSNR, that is our metric, in order to monitor the trend of the good signal with respect to the noise. From the evaluation section, we can check out that after 100 epochs, the subject is still strongly blurred and the noise is high, reaching about 16 as PSNR value. After 1000 epochs, the shape starts to be smoother and noise is going to be minimized, reaching about 21 of PSNR value. I decided to push the training phase up to 10,000 epochs, taking about 3 hours of time, reaching a peak of 26 as PSNR, considering also my GPU availability. I had just one allocated randomly between a K18, a P100 and a Tesla T4. After all, such model is trainable potentially for more, and it probably would work better, but I had the limitation of RAM. Thank you.